Put it in. Awesome. Good for y'all. So I'll actually, now I remember I have a video to show you. It's about 10 minutes long that kind of compares and contrasts these two types of compounds. Slides too. So a compound is atoms that are stuck together, and we use the formula to represent what atoms are stuck together and how many of each. So that's stuff you probably already knew. And so as the atoms stick together, there are two options. There is this thing called a covalent bond. A covalent bond I have up here where electrons are shared, okay? And then there's the other one that's called an ionic bond. And I have a little video here to show you. It's a video day. A little video to kind of show you how like sodium chloride would do that. Up here I have, and I got this from the video, in order for an ionic bond to form, an electron is going to be transferred. Specifically, find your JAG. Electron will go from your metal atom to your non-metal atom. Okay? So let's take a look at what sodium chloride does. 2 or 3, and I'll kind of talk about how many electrons a metal might want to give up. And the non-metal will accept an electron or 2 or 3. And so we have names for these things, and they're kind of small here, but can you see just the subtle difference in the spelling here? The ion, the positive one, is called a cation. Anything positive are metals kicking off electrons, becoming positively charged. We call that, it's not cation, it's a cation. And then things that the nonmetals taking in electrons will become a negatively charged species, negatively charged ion, we specifically call an anion, not to be confused with an anion. Okay. And then once they have a different charge, then they have this attraction for each other we call actually an ionic bond. So why do they do this? Why does sodium kick off an electron? Why does chlorine take in an electron? And actually, I think we talked about this before. We said that we talked about the word valence electrons. And valence electrons, if you're like, where did we come up with that? Actually, the group number, if it's a main group element, has the A with the group, then the group number is equal to the number of valence electrons, just for the A's. Okay, so here's the deal. Let's pick on chlorine. So if you find chlorine on the periodic table, if you find it on the periodic table, and if it's a group A element, which it is, you have a fighting chance for knowing how many valence electrons it has. So chlorine, these are our halogens. Our halogens are in 7A, so it has 7 valence electrons. So actually picking up 1 electron now gives it 8, and that's kind of what this is referring to. All atoms want 8, and that's why electrons are transferred. We talk about why electrons are shared. That's why they're shared also. Sodium's a little bit different. If we go over here to sodium, it's also an A group, so we can use the number to know the number of valence electrons. So it has 1 valence electron, and it's a little, not quite as intuitive, but in kicking off that 1 valence electron to become a +1 charge, it actually now has 8. So that's kind of how that works. So the metals are going to kick off all of their valence electrons to get that complete 8, what we call an octet. One of the things that Hal talked about was this idea of, I call it a tug of war. Electronegativity was the word he used. In science, a lot of times we'll throw in Greek letters, so I apologize in advance. This right here looks like an X. Actually, that is the Greek letter chi. C-H-I. Okay, and when I talk about electronegativity, I really think of a tug of war. So he talked about electrons being shared equally or electrons being shared unequally. By golly, if they're being shared between 2 atoms, you know that you have a covalent bond instead of an ionic bond. Okay, so what this tug of war looks like is, let's see what I have here. Okay. So if I have atom A and atom B, B isn't boron, it's just any atom, and here's my atom B, and they are stuck together by, somebody tells me that that little bridge, that little chemical bond, is a covalent bond. Well, I know that then we don't have ions involved, electrons aren't transferred. I must have electrons being shared there. But here's the deal, they might not be shared equally. So the electronegativity value, and we're going to kind of see it on this slide or on the next slide, says in that tug of war, by the way, if I see that kind of dash between those two atoms, I need to think of actually a pair of electrons or two electrons being shared. The one that has the higher electronegativity value, let's just say B. Let's say B, this guy. Let's make this an electronegativity of, let's make it 4.0. And let's say we look and we find the electronegativity of A, let's make it 3.5. Those are both pretty high, 3.5. In this scenario, they're not, the guy with the higher chi, the guy with the higher electronegativity value, he's actually going to be more negative. So this guy is going to be more negative. What do I mean? Or why is he more negative? He's more negative because he has more electrons drawn to him, or electrons are drawn to him more. And so actually, this is a polar bond. Okay. Let's see what else I have here. The greater the electronegativity an atom has, like B, we gave B a chi value of 4.0. Chi, that little X thing, that's electronegativity. We gave electronegativity value of 4.0 versus electronegativity value of 3.5. So in this case, B is actually going to be more negative. But not an ion. It's not going to be an anion. It's just going to be more negative. So in the ones that I picked, for instance, you know, B could have been fluorine, and let's see, 3.5. So this was an imaginary one, but these are the electronegativity values. If you, and I know they're kind of small for you to see, but the scientist Linus Pauling actually established these electronegativity values, and he got a Nobel Prize in chemistry for it. So sometimes these are called Pauling values. Notice the trend in electronegativity. By the way, the pink, hopefully you recognize the pink are our non-metals, and we're kind of showing you here, the blue would be some metals. Okay. So the metals have low electronegativity values. They actually say, in the tug of war, the metals with the low electronegativity values are like, dude, you can have the electron. I want to form a cation anyway. So in science, so you recognize hopefully this little X thing. That little X thing is electronegativity. It's the Greek letter chi. In science, and we're going to see this when we talk about physics too, they'll use another Greek letter that looks like a triangle. That other Greek letter that looks like a triangle actually is the Greek letter delta. If you're into sororities and fraternities, sometimes you'll hear these. Delta, chi, I don't know. Anytime you see the triangle or delta, that means change in. Change in. So now we're talking Greek here. If I see delta chi, that means, guess what? Change in electronegativity. Change in electronegativity. And probably more to the point, it's actually the electronegativity difference. Electronegativity difference. Goodness. In that example I gave with the A and B, so, and by the way, sometimes if you guys haven't done much with math, or if you have done a little bit with math, maybe you recognize these big lines right here that you see on either side of the delta chi. That means absolute value of. So I'm not a math teacher, but that means if it's negative, you make it positive. If it's positive, you leave it alone. So we're looking for the absolute value of the difference. So again, back to that example I had on the previous slide, the delta chi would be what? Absolute value of 4.0 minus 3.5. So your delta chi or electronegativity difference would be a 5. So, and Hal kind of mentioned this. We have these kind of different kind of flavors of covalent bonds where electrons are shared. So, so large differences in electronegativity differences, large differences between electronegativities of the two atoms mean that electron will be transferred, your bond will be ionic. Subtle differences, electron's going to be shared, so you'll have some sort of covalent bond. So, but we have these options. If your delta chi or electronegativity difference is 0, that means that your electronegativity values of your atom A and atom B are the same, and so they're shared equally. Electrons are shared equally, and so we call that a nonpolar bond. And I think he even said, I'll put E superscript negative sign, shared equally. But then we have these kind of differing kind of degrees of polarity or strengths of polarity. If they're not shared equally, which was the case between my two atoms, okay, I had an electronegativity difference of 0.5, I would look at that chemical bond, that covalent bond that's between those two atoms, and I would say it's weakly polar. If you're kind of bump up the difference, the tug of war is a little more extreme, okay, then we say that it's a polar covalent bond. 1.2, strongly polar. Now, about 1.7, if that's the differences between your tug of war sort of going on between your two atoms, then actually an electron is going to be pushed from the one with the low electronegativity value to the one with the higher electronegativity value. And you'll have a cation and an anion. But these first 4 up here that are listed, keep in mind that electrons are going to be shared right up to the point where they're not. Okay, electrons will be shared but not shared equally. So these first 4 are all types of covalent bonds. Electrons are shared. So I've got some scenarios to kind of show you what that would look like. If your electronegativity values are the same, this is atom. Let's see if you can kind of picture what this is trying to show. The gold actually is trying to show you how the electrons are kind of in a cloud. What you need to think of this is hiding in that gold. That's the nucleus of atom A, that's the nucleus of atom B. One of the things we know about atoms is they have, in the center they have the nucleus, and the outside they have the electrons. And it's the electrons that help stick them together. So in this case, electrons are shared equally. In this case, an electron was transferred, and we kind of did this with sodium chloride. Notice that the cation, the thing that becomes positively charged, becomes smaller because it lost an electron from its cloud outside the nucleus. The thing that picked up an electron became negatively charged and becomes larger. Just to kind of make sure we're on the same page, I would call this +1 a cation, and sometimes you think cat, it's got the T, you're crossing the T, it's positively charged. An electron was transferred, I'll put a little E, kind of going from the blue one to the gold one, and then this is what we call an anion. And then part of this discussion, we've introduced kind of the idea of polarity. So this one, can you see the word polar? Polar means, think of polar as, well, if you have a polarizing personality, that means that people can really like you and people can really not like you. You kind of polarize the crowd you walk into. So along those lines, if we're talking about a polar bond, it must be a polar covalent bond where electrons are shared. But I can see that gold one is a little bit bigger, okay? And actually that, another Greek letter, I think this is I'm not sure which Greek letter this is, but this Greek letter, if you ever see something like that in science, that actually means partial. Okay, a lot of Greek this morning. So when I look at this symbol up here, I have a partial negative. And here, the blue, I have a partial positive. Partial meaning, hey, an electron didn't really jump ship, but it's living more, okay, over on the left atom. So making the left atom partially negative. A really good example of this, where this polarity is so important and it has lasting effects, is a compound near and dear to all of our hearts, water. Because water molecule looks like this. It's H2O, obviously. So H2O. So here's my oxygen, and here's my two hydrogens. Okay? And if I go back and look at the Pauling values, I could describe that situation between that oxygen and that hydrogen. So what I would do is I would compare the oxygen's 3.5, tug of war wise, electron kind of, and a hydrogen is 2.1. So you can see that actually oxygen is going to pull electrons to itself, and hydrogen is going to lose in this tug of war. We can calculate the electronegativity difference, the delta chi. And I usually put the big one first so I don't have to do much thinking. So oxygen 3.5 minus 2.1. So you're looking at electronegativity difference 1.4, which is pretty big. So on this water molecule, and this is significant, the oxygen, it's a tug of war, and that's what we call partially negative, and both the hydrogens are partially positive. And the important thing, I'll go ahead and just kind of finish that thought, where polarity comes into play is if I have another molecule, let's just say I'm drawing another water molecule down here, because those three atoms are stuck together and they're not going anywhere. And this is a partially negative, because that's what oxygen atoms do in water. We have two partially positives here. Actually then, between these, and I'll switch to maybe red, between these two water molecules, there will be a dot, 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 dot. And that's not a chemical bond, but that is what we call a hydrogen bond, and that's very strong. Right there. I'll put H for hydrogen bond. So just to kind of make sure we're all on the same page here, I'll kind of outline the water molecules. So the polarity of water makes that a crazy sort of deal, that hydrogen bond between two water molecules. And it all has to do with kind of the electronegativity difference. So here's some other kind of examples. I think Hal used the example of chlorine, of two chlorine atoms stuck together. If I was to look at the electronegativity difference, the tug of war between those two chlorine atoms would be like 0, because they both have the same Pauling value, electronegativity value, chi value. By the way, I think I talked about this, and I get my classes confused sometimes, but chlorine is one of those special elements. There are 7 elements that are diatomic, and if you do the name, I don't know if this rings a bell, Hofbernickel. Oops, sorry. I'm back. Okay, and I can put little subscripts too there, saying that all hydrogen atoms like to have another hydrogen atom stuck to them. They come around 2s. All oxygen atoms 2s, fluorine atoms 2s, bromine 2s, nitrogen 2s, iodine 2s, and chlorine 2s. That's just what they do on normal temperatures and pressures on Earth. So chlorine is one of those diatomic elements. That was my point here. Sodium chloride, the tug of war is such that if we go back, if you look in your handout, the Pauling values for nitrogen and chlorine, sodium and chlorine, my bad. I'll go over here. Okay, sodium chloride, sodium and chlorine. The electronegativity difference, the delta chi, is equal to the absolute value of the difference in electronegativities. So chlorine is 3.0, and sodium is 0.9. So you're looking at what, 2.1? So a little bit ago I said if it's 1.7 or greater, an electron's going to jump ship. 2.1, that's greater than 1.7. So that's kind of how that works. The bond between a hydrogen and a chlorine atom in hydrogen chloride, actually if you do the math, you're going to see that electrons are shared but not shared equally. Chlorine's bigger, that's going to actually be partially negative. The hydrogen's going to be partially positive. So this will be due when we meet again, and we're going to kind of ease on into the next part. I think while I'm thinking of it, I think I mentioned this, but Thursday, make sure no matter how nice and warm it is outside, everybody has to have their feet covered because we're going to be doing our chemical reaction lab. So these will be due on Wednesday. Lab on Thursday. All right. Don't mean to jinx you guys or anything, but you guys have been doing really good at turning in your homework. Thank you. That's a good thing. So keep up that good work. Okay. So when I pick and choose, and actually your textbook's pretty much in track with what I would pick and choose too. One of the things I want to talk about is this idea of switching gears to ionic compounds. And I want you guys to have a sense for how are they put together? Okay. Now the word binary here just means, I want to talk about ionic compounds where you only have two elements that are binary, two elements that are stuck together. Now, when we talk about ionic compounds, ionic compounds, I said one atom has to be a metal. So guess what? The other one's going to be a non-metal. A good example of something I kind of want us to become familiar with is like sodium chloride, NaCl, okay, a binary ionic compound. If we pick on sodium chloride, that's a good example. If we pick on sodium chloride, one of the things in knowing, well, how do I say this? Well, I'll just start up here with water. Most people would tell me the formula for water is H2O, right? H2O. That means I have two hydrogens and one oxygen. Sometimes people tell me what's table salt. Well, you say the formula is NaCl. That means I have one sodium and one chlorine in that formula unit, okay? So here's the deal. In having one sodium and one chloride, we make it neutral. I'll show you what I mean. Sodium is going to form a +1 charge. We'll talk more about that. And chlorine is going to form a -1 charge. And if I have one of each, I can kind of see how, if I have a neutral formula unit. So I have one sodium, and it's a +1 charge, and I have one chlorine, and it's a -1 charge. And again, I'm not a math teacher per se, but I'm kind of liking that all adds up to be equal to 0. And that's what we mean by, if you write the formula of an ionic compound, you need to have the right number so it actually makes it, your pluses and minuses cancel. Makes it neutral. Okay. So one thing about it is if you write the formula for an ionic compound, you don't say what the charge is. So somebody wouldn't tell me that it's Na plus Cl minus. And I'm going to show you actually how we can find those on the periodic table and know that it would be Na plus 1 and Cl minus 1 from the periodic table. But we don't show the charges. Usually we have the metal first, which is going to be a cation, and then the non-metal last. And we're kind of doing that pattern with NaCl. Okay. So not only do I want you to be able to write the formula for an ionic compound where the pluses and minuses cancel out, where it's what we say neutral, but I also want you to have a sense of how you're going to name it. Table salt, people usually tell me it's sodium chloride. And you're right. So the first name is just going to be the name of the metal, sodium, Na, sodium. The second name, actually, is going to be the non-metal, where you take the non-metal's name. So non-metals, where we got non-metals? We got non-metal over here. You take the non-metal's name that you've got to be kind of familiar with, because I said you need to know, be able to tell me what the name of some of these are. And for instance, chlorine, you lop off the end, the INE, and instead you replace it with IDE. So instead of sodium chlorine, it's sodium chloride. So again, the first name stays the name of the metal. The last name, which actually is going to be, in the case of what we're working on, the non-metal, you lop off the end and you replace it with IDE. So I think I have a slide coming up to kind of show you what that looks like. So hold that thought. Let's kind of look at what this whole neutral stuff would look like. I'll try to kind of, see, I can't remember. I can't remember if we've gotten this far. Oh yeah, this works. Okay, so from the periodic table, those little dots represent valence electrons. Sodium, you know valence electrons from the group number. Sodium, it's A, it's 1A, so that one dot is its valence electron. Sulfur, let's find sulfur. Sulfur's over here. It's 6A, and so we have 6 dots around it. So what happens is the sodium is going to kick off its valence electron. The sulfur is going to take in 2 electrons. And in doing so, the sulfur, okay, now collectively has a -2, it's a -2 anion, and each of those sodiums are +1 cation. So can you see, and I'll take my marker and kind of write it underneath there. So this right here, how do I say this? So I have 2 sodiums, and they are both a +1 cation, and I have 1 sulfur, and it's a -2 anion. And then if I do that math, I'm liking it's 0 charge. So that's what we mean by neutral. Notice if I went a formula of NaS, that wouldn't work because I'd end up with just kind of looking in my head, I'd end up with a -1 charge. So I need it Na2S because I need 2 of those +1s. Okay. Let's look at another example. Magnesium chloride. And again, I'm going to kind of show you how we know this. Magnesium, well, we kind of know how we know this. Magnesium, if we find it on the periodic table, it's the metal over here, kind of on almost the far left. So magnesium, if we backtrack to what group it's in, it's an A, so we can actually use its group number, which is 2, to know how many valence electrons it has. It's going to kick off 2 valence electrons, and in doing so, it's going to become a +2 cation, just like you see up there. Chlorine, over here, 7A, pick up 1 electron, okay? It's going to become a -1. So that's why the formula for this one, if we do the math, you need to have 2 chlorines to basically level out the 1 magnesium. So what this looks like is I have 1 magnesium, and it's a +2, and I have 2 chlorines, and they're both a -1. So yeah, that's neutral as it's written like that. You guys already have these. Silly me. So instead of oxygen, it's oxide, nitrogen, nitride, sulfur, sulfide, chlorine, chloride, hydrogen, hydride, bromine, bromide. I almost feel rude, bromide, phosphorus, phosphide, fluorine, fluoride, and iodine, iodide. So, I've been kind of telling you how to do your cheat sheet for this test. I don't know, you might put those on your cheat sheet. You probably got room for them. I'm just saying. And if you do that, I would also, while you're at it, go ahead and give the elements and what charge it forms. So these are all our non-metals picking up an electron to electron 2 or 3 to get what we say the rare gas at the end of the period. So that's a good place to break. We'll pick up right here in when we get on Wednesday, first April.